This is Mr. Hassan's Maths channel, and I'm now answering question number 3 from the June 2014 International A-Level Mechanics M1 paper from Edexcel. And this is a question I've answered part A before some years back. Very bad recording in terms of the sound quality. And some students have been asking me to do part B in this question. So I have decided that I would do part B and C, okay, which is over here, B part 1 and 2. And I've also decided that I will just do part A again because of the lack of quality in the sound. It was when I first started making my videos, and I didn't have a proper mic and setup. So now it says a particle of a P of mass 1.5 kilograms is placed at a point A on a rough plane, which is inclined at 30 degrees to the horizontal. The coefficient of friction between P and the plane is 0.6. Show that P rests in equilibrium at A. So basically, they gave us this diagram here. Okay, and that was, like part of part B. So we have to look at this diagram as if there's no force here X acting. Just the particle P resting on the plane, and that's it. Okay, that's the only, there's no other force apart from the obvious forces of friction and the weight which will be acting on the particle. So I've got like a copy of that same diagram, but without the force acting horizontally. For part A, we don't need to consider that. So for this question here, we need to make a clear diagram, force diagram. So this is the point A where it's resting, and we have to show that it's going to stay at point A. So now what I'm going to do is I'm going to draw the forces acting on the particle. And of course, you can say that its weight acts vertically downwards always. So that's its weight, and its weight is 1.5 times G, newtons. That's the weight acting vertically downwards. And it's in equilibrium at A because, of course, there must be friction acting. Well, friction is always acting in a direction to oppose the motion. If this was on a smooth plane and there was no friction, this would slide down the plane. So the friction is what's preventing it from sliding down the plane. Okay, so the friction is going to act upwards. Okay, so you have a frictional force. Okay, so that's frictional force. Okay, I'll just call it F. I'll confuse people there. Okay, and we also have the reaction force acting when an object is in contact with the surface, which is always perpendicular to the surface. So that's going to be at right angles to the surface, and that's the normal reaction force, which we could call R. So those are the forces acting on this particle. Now what we need to do is we need to resolve these forces parallel and perpendicular to the plane. Okay, let's just talk a bit about the situation. So this particle is, we have to show that this is resting in equilibrium. So basically what we have to show is that the component of the weight acting down is less than F max. F max would be the maximum amount of friction that can be generated in this situation. Okay, so as we should understand, when you have a rough surface, for example, let me just take it back to the origins and just give a little explanation about friction. If you have a rough surface and you have some sort of block which is resting on this rough surface, okay, and there's no force being applied onto this block at all. It's just completely still. Okay, in that case, the friction will be 0 because it's not trying to move. However, if there's a force acting in this direction, if there's a force acting in this direction, and for example, that force is say 5 newtons, okay, then the frictional force will be acting in the opposite direction to oppose the motion. Okay, now if the frictional force can reach a value of 5 newtons, it will equal 5 newtons. Okay, if this becomes 10 newtons, then this will become 10 newtons. If this becomes 15 newtons, then this will become 15 newtons. It just does enough to match the force that's trying to pull the object along. Okay, that's what friction does. However, supposing this cannot go more than 15 newtons, supposing the maximum value of friction, F max, is equal to 15. Okay, in this particular situation with, the roughness of the surface and the reaction force here, if that's the maximum can ever reach the frictional force, and this becomes 16, then it's going to start accelerating. There's going to be a resultant force acting in that direction, and it's going to start moving. It won't be in equilibrium. It will stop being in equilibrium as long as the frictional force cannot match the force that is trying to make it move. All right. So we have to basically, as long as the frictional force, the maximum value of friction, F max, is greater than the force that's trying to pull it, then it will remain in equilibrium. Or you can say the other way around. If the force that's trying to make it move is less than F max in that situation, then it will be in equilibrium. Okay. Less than or equal to F max. Okay. So we have to show the force acting down the plane, okay, is less than or equal to the force that the maximum value that friction can take. Okay. The frictional value that can be generated in this situation. Okay. Because the frictional force only matches what's going down, keeps it in equilibrium. That's what it tries to do until it cannot go higher. If it cannot go higher than the force pulling it down, then it's going to start accelerating. And this will remain at F max. So we need to calculate F max. So we have to resolve some forces first. So let's take this perpendicular and parallel to the plane. So now I'm going to just resolve the forces in this direction and that direction. Now, one of the things that a lot of students ask about is this angle here. Why is it the same as the angle to which the plane is inclined? Why is this the same as 30? Some students don't understand why, and they ask why. And I'll quickly show you why. We can consider this big triangle here. This big triangle here has an angle of 90 degrees because this is, perpendicular to the plane. And it has this angle here, okay, in this corner. And this is angle 30. So the big triangle looks something like this. You have a right angle. You have this angle over here, a right angle, and 30 degrees. Now, if we take this little triangle here, I'll draw it outside. This little triangle here. There's a 90 degrees here because that's vertically down. All right. This angle is the same as this. Well, we're going to prove it, but this angle is the angle over here. And this angle here is the same as the angle over there because they represent the same corner in the big triangle and the small triangle. So these two angles are the same in both triangles. So the third angle must also be the same by similarity, angle. If this angle is 90 and this angle is the same as this angle, this is 90, this angle, these two angles are the same. Of course, 180 minus the sum of those two will give us the same. So that must be 30 degrees. So that's the reason why the angle to which an object is, plane is inclined, the angle between the inclined plane and the perpendicular line to the inclined plane is exactly the same as the angle to which the plane is inclined in the first place. You don't need to prove that, but just some students they like to find out and ask why. Okay, so let me just get rid of some of the things I use there. All right, so now we're going to resolve the forces parallel and perpendicular to the plane. So I'll just use a different color and a dotted line. So I'm going to take the weight and I'm going to resolve it perpendicular to the plane, and I'm going to resolve it parallel to the plane. Okay, so if I want to resolve it perpendicular to the plane, then we've got to think about, as I mentioned many times, we're going to go into the angle. Okay, if we think about it in terms of, what maybe you're used to, like this is parallel to the plane and this is perpendicular. So if we're going to resolve it in this direction, we're going to need the adjacent side. This is like the force on the hypotenuse is adjacent, so we're going to use cosine. Or if you go into the angle given, use cosine. So this is going to be 1.5 g times cosine 30. 1.5 g times cosine of the angle 30. And if you want to resolve the forces parallel to the plane, then we're going away from the angle given. Okay, or you can think of it, we're trying to find this opposite side, which is parallel to that, which is going to be opposite, is going to be sine. Okay, so we use 1.5 g, which is the hypotenuse, times sine 30. 1.5 g times sine of 30. So now we have resolved all the forces parallel and perpendicular to the plane. Okay, so these red lines are the weight resolved parallel and perpendicular to the plane. Now we can start considering what we mentioned earlier about the value of F max as compared to the value of the force that's acting down the plane. So this is in equilibrium. We have to prove that's in equilibrium. And it's in equilibrium if, as we mentioned before, that the maximum value of friction, okay, is, let's put it the other way around, as long as the component of the weight acting down the plane, which is 1.5 g times sine 30, if this is less than or equal to F max, then it will be in equilibrium. Okay, so if the force acting down here is less than or equal to the maximum value that friction can be generated in this situation, then it will be in equilibrium. So right now, we cannot say F is equal to F max. We don't know until we worked out what this is, and until we worked out what the maximum value of friction can be. So what we're going to do here is we're going to work out what is a maximum value that friction can take in this situation. Now we know that that's given by the formula mu times r. There's two things that affect the maximum value of friction. One of them is the coefficient of friction, which is telling you about the roughness of the surface, and the other one is the value of the magnitude of the reaction force. Okay, so now we got to work out the magnitude of the reaction force, which in this case is pretty simple. It's just going to be, if we resolve the forces perpendicular to the plane, which we've already done, so we have R is equal to 1.5 g times cosine of 30. All right, and we know that mu is equal to 0.6, which I'll write as 6 over 10, which is 3/5. So therefore, we can say F max is going to take the value of 3 over 5, which is 3/5 times 1 over 1.5 g, so that's 3 over 2 times g, okay, times cosine 30, which is root 3 over 2. So I've just tried to keep things in exact form for now. So I have, that's 3 times 3 is 9 times root 3 over, that's 5 times, so over 20 g. Okay, so I'll write this also as a decimal so we can compare it easily. Okay, so 9 root 3 over 20 g. So I have 9 times root 3 over 20. I'll just keep it like this and then put it in terms of g. That's going to give us 0.7794, 0.7794 g, which is 0.779 g. Okay, that's F max. All right, and then we got to work out what 1.5 g sine 30 is. 1.5 g sine 30 is going to be 3 over 2 times g times a half, which is 3 over 4g, which is 0.75 g. And we can see that, you know, as, okay, 0.75 g is less than F max, okay, which is 0.779 g, okay, therefore the object will stay in equilibrium. Okay, therefore we can say P rests in equilibrium at the point A. Okay, so there's the answer to part A of this question. Yeah, so it doesn't mean that the frictional force acting is this much. And this situation, the frictional force is exactly the same as this. These two are equal. This is equal to 0.75 g. That's what this is equal to at the moment. Because this is 0.75 g, that will be the same. That's why it's in equilibrium. Okay, it's just matching this force. But the maximum it can ever reach is 0.779 g. That's the maximum it can get to, right? And if this goes more than that, then it will stop being in equilibrium, right? So as long as the component of the weight down the plane is less than or equal to F max, it will be in equilibrium. As soon as that increases over F max, it will then not be in equilibrium and it will start sliding down the plane. Okay, so there's the answer to part A, which I've revisited after all these years. Now I'm going to go on to part B, part 1 and 2, which is what the students were asking me for on the channel. So I'm going to go through that now. Okay, so it says here, a horizontal force of magnitude x newtons is now applied to P as shown in figure 1. This is figure 1. The force acts in a vertical plane containing a line of greatest slope of the inclined plane. All right, some people don't understand what that means. Just imagine we're looking at this from this direction. Okay, this is someone's eye looking at this from this direction. kind of make a 3D little diagram, they'll be seeing kind of like the plane like this. And this force is acting kind of in a direction which is like in line with, kind of like in line with the plane. So it goes straight up. Okay, it's not acting at an angle. It's not acting at an angle to the plane this or this way. It's acting like, along the same plane, straight, or it's not hitting at an angle. It's not like an arrow is hitting at an angle. It's going straight into it. Something like that. So that force is acting in such a direction that it's going to be acting, okay, straight up the plane. Okay, it's going to be acting in a direction which is like, parallel to that shortest line going up the plane. Right. So that's basically what that means. And the particle is now on the point of moving up the plane. Right. So now, very, very important phrase. On the point of moving. Whoops, what happened there? On the point of moving means something very important. On the point of moving up the plane. So it's in limiting equilibrium. This is called limiting equilibrium. Limiting equilibrium. Why? Because it's just about equilibrium. Okay, it's just about to leave being in equilibrium. It's in the limit of its equilibrium. It's just about to start moving. It's on the point of moving. All right. So basically that means F max has been achieved. X max has been achieved. Now in this case here, the mistake that people make is they will use the same F max as we did in part A. In this case, there's another force acting which will affect the value of the reaction force, which will cause F max to have a different value. Okay, so be very careful about that. Be very careful about that. Okay, so don't use the same F max in part A because there's other forces acting will cause R to be different, which will cause F max to be different because F max is equal to mu times R. We know mu is still 0.6. Okay, the coefficient of friction, but the R will be different now. So be very careful about that. So now, if we look at the forces acting on this particle, we now have to consider a few other things now. We have to consider the fact that, well, we've still got the weight. We've still got the reaction force. Okay. Now, what I like to do in these type of questions, so the weight was, what was it again? 1.5 G, right? 1.5 G, same particle. That's 1.5 G newtons acting straight down. Now, with a force like this, to make it clearer, a lot of students don't know how to resolve these forces. Okay, to make it clearer, what I like to do is I like to take this force and just draw it slightly further along. So I'm going to take this X and draw it, on this side. Okay, it's the same direction. It's exactly the same. It's still X. I've just drawn it this side to make it a bit easier for myself, right? That's what I like to do. So let me just get rid of this so this doesn't confuse us. Okay, it makes everything easier when I do this. I prefer to do it this way, as you'll see, because now I know this angle is 30 degrees. I know it's going to have a component up and also a component into the plane, perpendicular to the plane, into it. So let me just do the resolving of the forces. Now I have an extra force to consider when I'm resolving the forces. Okay, so I'm going to draw this little line here again. Okay, we know this angle is 30 degrees as we discussed earlier. Okay, and I can have my forces now in a different color. So I have my weight component down the plane, or perpendicular to the plane and parallel to the plane. Okay, so those are the components of the weight. But we also have the components of X. It's going to have a component parallel to the plane and also a component perpendicular to the plane acting downwards. That angle is 30 degrees, as we can see from parallel lines. This is horizontal corresponding angle. So that angle is 30 degrees as well, right? So if I resolve the weight parallel to the plane, I'm going to go away from the angle as we discussed before. So 1.5 G times sine 30. And here you'll have this one, 1.5 G times cosine 30. And here you're going to have, this will be X times, and we're going away from the angle, that's going to be sine 30. Because we're going away from the angle. It's like we're finding the opposite side. Okay, and here we're going into the angle. So we're going to have x times cosine 30, right? So if I want to now find the magnitude of the normal reaction on the plane, I've got to resolve the forces perpendicular to the plane. Okay, so perpendicular to the plane, you have R, and then you have, because it's in equilibrium, the whole thing anyway, R equals, okay, you've got 1.5g times cosine 30 plus, because this is also acting down, x times sine 30, okay, and now we have a couple of things unknown. Let me just put these in terms of this. So 1.5, 3 over 2 times g times root 3 over 2 plus a half times x. So we can say therefore r is equal to 3 root 3 over 4 g plus a half x. That's one equation we've formed. And if we resolve the forces also parallel to the plane, okay, so you can do it either way because it's in equilibrium. I like to do it like it's on the point of moving up, so I'll put up the plane as positive. The direction in which it's trying to move, but it doesn't really matter because it's in equilibrium. You'll say x times cosine 30 times cosine 30 is equal to, and you're going to have 1.5g. There's one more thing we have to consider, very important here, which I didn't mention. Now, it's on the point of moving up the plane. What does that mean? What that means is that there's going to be a frictional force acting as well. Okay, we know it's a rough plane, so friction. Which way does friction act? Now, we know that F max is going to act. We mentioned that already. Which way does F max act? Okay, it's going to be parallel to the plane, but which way is it going to act? Well, if it's on the point of going up the plane, then friction is trying to prevent it. So F max is going to be acting down the plane, and we know F max will be actually reached because it's on the point of moving. So it's on the limit of its equilibrium. So F max has been achieved, okay? And it's acting down. Why? Because the object's about to move up. All right, so before we resolve the forces parallel to the plane, we have to consider the fact that you've got x cosine 30, which is the force trying to make it move up the plane. And that's equal to the downward forces down the plane, parallel to the plane, which is 1.5g sine 30, okay, plus F max. Okay, so we know that F max is acting now. How do we find F max? Well, we have to combine these two equations together. So let me just simplify this. Cosine 30 is root 3 over 2. So root 3 over 2x equals 1.5, which is 3 over 2, times sine 30, which is a half. So that's going to be 3 over 4g plus F max. Now I know F max is equal to mu r. Okay, which is equal to mu r. We know F max is equal to mu r, and we know that mu is equal to, as we were told, 0.6. Okay, so you're going to have here 0.6 is mu. So you're going to have plus F max, which is 0.6 times r. Okay, which you can write as 3/5. So as I've got fractions here, you don't have to put things in fractions. I like to do this. So 3/5 times r. So now we have these two equations. There's equation 1 and equation 2. We have two unknowns, x and r. So we can solve these equations simultaneously. So we could do it in a couple of ways. What would be the easiest way? I think just replace the r with all of this. Okay, so we're going to put equation 1 into equation 2. All right, so we have 3 over 2, root 3 over 2, sorry, x is equal to 3/4 times g plus 3/5 times r, which is 3 times root 3 over 4g plus a half x. So now we have got rid of the r from the equation, and we're going to find x. Okay, so we're going to do part 2 first and then part 1. It doesn't matter. Both of them are together as one question. All right. So now I'm going to find what x is. So I need to expand this. So I've got root 3 over 2x is equal to 3/4 g plus, that's going to be 9 times root 3 over 20g. 9 times root 3 over 20g plus 3 over 10x. Let's bring the x's together. So root 3 over 2x minus 3 over 10x equals 3/4 g plus 9 times root 3 over 20g. So if we just take x out as common from here, we have root 3 over 2 minus 3 over 10 equals 3/4 g plus 9 times root 3 over 20g. So therefore, x is equal to all of this divided by that. I'm going to keep it like this because I much prefer to do this and write decimals and then, round them and stuff. I'll write this in this form, divided by root 3 over 2 minus 3/10. Okay, which gives us, so make sure we put this in the calculator properly. We have 3 over 4 times g. Okay. Yeah, I'll just put it in terms of g. 3 over 4 plus, I'll put in terms of g in the end because g can be taken out, plus, and you're going to have 9 root 3 over 20. Okay, that's all in terms of g, over root 3 over 2. Root 3, we've got to be careful about that, over 2 minus 3 over 10. Okay, so that gives us 2.702 g. 2.702 g. So if we multiply by 9.8, okay, that gives us 26.4799. 26.4799. So we should give our answers to 2SF or 3SF. 3SF is safer. So 26.5 newtons. That's X. And now we have to find what R is. So we can find R from this formula that we have here. R is equal to 3 times root 3 over 4g plus a half times whatever X was, which was, I'll write it in this more exact form, 2.702 g. Okay, so R is equal to all of this. So let's just, so we got, this is X in this exact form. What I have to do is multiply that by a half. So divide that by 2. Okay, and then this I have to add it to 3 times root 3 over 4 times 9.8. And that gives us 25.9705. 25.9705. So R to 3SF is 25 that's going to become 26.0. 26.0 newtons. Okay, 26.0 newtons. And that's the value of R to 3SF. Okay, so we found the value of X and R. Okay, so that's how we do it. It's a bit of a, the numbers are a bit awkward here. You could write things in decimals from the beginning, but don't write them to decimals to 3SF in your steps. Write them to more than 3SF, and at the end, round them to 3SF. I've kept things in more exact form until the end, and then got my answers. So this question is one about statics and limiting equilibrium. Very important question. Okay, so I hope that was clear. As I said, part B is a question that some students were asking about in the comments of my channel. So I've done part B and I've redone part A again, as it was an old recording. So other questions from this particular paper you can find in the playlist that will appear in the top right of this corner for this paper. Other questions dealing with statics from my Edexcel collection, you'll find over here in this particular playlist. And I will also put this in my inclined planes and forces and friction playlist as well, because we're dealing with friction, forces, inclined planes, and all that kind of stuff. Thank you for watching and see you soon.